Good evening. Welcome to the Canberra AWS User Group. I'd like to kick things off this evening by acknowledging the traditional custodians of the land that we're presenting from, the Ngunnawal tribe, and paying my respect to their elders, past and present. Welcome to the June Canberra AWS User Group for 2021. This evening, we're going to take you through a bunch of good AWS content, starting with some of what's been new in AWS this month, a usual look at white papers and training updates so that you can get some really good information. And then the main presentation for the evening is going to be Tony Hawke doing a deep dive into the AWS Gateway Load Balancer. So as always, I like to plug our YouTube channel and let everybody know it's there. That's a horrendously long link because I can't change it until more people subscribe. So please like and subscribe our YouTube channel. All of our content from March last year when we kicked off doing these things online is all available there on demand. So heaps of great sessions from lots of local presenters. So if you're interested in getting more AWS user group content, that's the place to go. What's new in AWS this month? There's been 135, so just a quiet month really, new features and updates that have gone into AWS this month, which for those of us who like charts like myself, looks a little bit like this. Let's kick off with some of these updates. So the first one I want to talk to you about is the Amazon Location Service. It's now generally available. Amazon Location Service is used to be able to build mapping functionality into your applications. So I can bring in maps and geofences and routing from A to B and give all this sort of functionality based on locations in the real world into your applications. You can choose different mapping providers. It's all really configurable and is a great experience as a developer to bring these kinds of real world locations and services into your applications. The next one is AWS Transit Gateway. This one has been updated with a new SLA. So the service level agreement for uptime on Transit Gateway has been increased from 99.95, 3.5 nines, to 99.99%, so 4 nines. Now, given that Transit Gateway typically forms a fairly critical part of your network infrastructure, more uptime in the SLA is a good thing. So CloudWatch has added 14 new metric math functions. So normally, CloudWatch has had the ability to do maths with your metrics previously, such as things like adding and combining them together. What these new functions do have some additional capabilities for things like handling sparse values to create more visualizations that are easier to see, as well as things like do rolling totals and counts on your metrics as you look at them over a time period. So if you've not gone back and had a look at some of the things that you can do with dashboards and metrics in CloudWatch, now's a really good time to get into that. Next, Amazon EMR Studio has been added to 13 additional regions, including Sydney. So EMR Studio, if you've played around with Elastic MapReduce at all, is an IDE that you can use to do things like authoring your Spark jobs and things that are going to be running inside of EMR. So you've got a really centrally managed IDE that has all the components that you need to build your EMR jobs out. Next, AWS announces the general availability of AWS Proton. So Proton was a new service that got announced in preview back in reInvent in November, December of last year. And what Proton is designed to do is to help organizations where you've got a separate IT team that wants to manage sort of core infrastructure and templates for serverless and container-based applications so that your developers can take approved templates of here's how the infrastructure side is done, and they can bring the developer side into it and then have things released in a pipeline for you. So if you've got an organization where you're not necessarily infrastructure and developers all in the one team contributing to the same application at the same time, but you've got separate teams and you want one managing the templates and the other managing your applications, Proton's a really great tool to bring into your workflow to help make sure that things work smoother and are more compliant in how you operate. Next up is the announcement of per second billing for EC2 instances running Windows and Microsoft SQL Server. So previously, if you were running Microsoft Windows or SQL Server EC2 instances that included their license as part of what you were buying from AWS, these were billed in per hour increments. So this was okay for static workloads, but it had some challenges for things like auto-scaling, where you might add instances for a portion of an hour and still be paying for that full hour. Now with per second billing on these, you're able to get a more granular billing and genuinely pay for what you use on those Microsoft workloads. Next is the announcement of the public registry for AWS CloudFormation. So if you've been playing around with CloudFormation, you might have seen the private CloudFormation registry was released a while back, where you can publish your own modules and resources that can be used by other people who have access to your account. Now, with a public registry, you can go through and get open sourced and third-party solutions that have been published to that public registry and really easily drag them down into your account so that you can use them in your CloudFormation templates and your CDK applications. So this makes it really easy, and there's a number of third parties that we've been working with, like I know Datadog and Atlassian are a couple that are in there, that you can bring their resources directly in without any additional work because they're in that public registry. So definitely worth a look. Next, one that's near and dear to my heart, Amazon CodeGuru Reviewer announces CI/CD integration with GitHub Actions and new security detectors for Java. So two things for CodeGuru here. First of all is the GitHub Actions piece. So if you use GitHub, you've probably played around with GitHub Actions at some point, which is essentially a task runner sort of CI/CD mechanism that you can build into your GitHub repositories. Now you can incorporate the CodeGuru scanner into those actions. So I can literally just put it into my actions file, commit it into the source repository, and then GitHub will go through and do the analysis in CodeGuru for me. Now, the really great part about this is it will bring the results of that CodeGuru scan back to you in GitHub. So you'll see them under the code scanning section in your GitHub repository. And this means that I can have all of the benefits of CodeGuru and what it's doing in terms of scanning my repositories without even leaving GitHub. I don't even need to sign into an AWS account. I can do it all in that one screen. So it's a really great feature for those who are using GitHub. The second one was the additional security detectors for Java. So again, there was already an initial set of security-related detectors in CodeGuru. These have been extended to be able to include more functionalities and look for different types of issues. So a couple of examples there are encrypting values on all paths. So if you encrypt something with KMS on one code path, it'll make sure that you're encrypting it on all of them. And there's a bunch of other ones there. And the last one I wanted to talk to you about was a bit of a fun developer one called AWS Bug Bust. So Bug Bust is a new service which builds upon some of those ones like CodeGuru Reviewer and Profiler and brings it together in a way that gamifies a bug hunt. So you can go into Bug Bust, create yourself an activity where you set up a private bug hunt for your team, and then using CodeGuru Reviewer and Profiler, find bugs in your applications, and you'll have like a leaderboard for who's fixed the most bugs and tracking all of these sorts of things, and be able to participate in a global competition. So what we're looking to do is help eliminate $1 million worth of technical debt in all sorts of Python and Java applications around the world. And to help make this competition a little bit more interesting, there's prizes for everyone. So if you participate and get a certain number of points from bugs you've helped resolve, you get things like t-shirts or jackets and trophies, or for the top 10 around the world, there's all expenses paid trips to reInvent. As always, terms and conditions are on the website for the competition, so absolutely go and check those out. But Bug Bust, if you do sort of bug hunt activities, is a great way to be able to gamify that within your AWS account. Okay, so in terms of training updates, as always, aws.training is the website you want to go to for all of our materials. This month there was an updated classroom course around AWS Tech Essentials, and there was also a new digital course around how to improve your code quality with CodeGuru Reviewer. For white papers this month, there was 16 new and updated white papers, a couple that I wanted to call out as far as highlights. There's the AWS Security Incident Response Guide got an update. So if you're in the security space, seeing the updates for that is always one you want to stay close to. The Amazon Workspaces Cost Optimizer, there's a reference architecture diagram for this. So if you're an Amazon Workspaces customer, being able to look at the metrics and determine have you right-sized those instances can save you some money. And so this is a tool that can help you do that. And this white paper will talk you through how the tool works and how to deploy it. And lastly, there was a new one around unpicking vendor lock-in. So it sort of talks to the concepts of what vendor lock-in is and what actual costs you might face in terms of trying to move workloads from one cloud provider to another. So if that's something that you're concerned about, this white paper is one that is worth checking out as well. On that note, though, I'm going to hand over to Tony for the main presentation, and we'll see if the audio has been holding up. Over to you, Tony.
Excellent. Thank you, Brian. Good evening all. Let me just change to my slides. So, hi there. My name's Tony Hawke. I'm a network specialist TAM in AWS Enterprise Support, and we're going to run through Gateway Load Balancer tonight. So, just a quick overview to give you an intro into what Gateway Load Balancer is, how it works, show you a few example architectures, and then do a bit of a demo. So, first up, AWS customers use third-party appliances. This is obviously the biggest bombshell of the night for everyone. We define here an appliance as any virtual network function running on an EC2 instance. The most common that we see is a network firewall or an IDS, IPS. We also see some DDoS prevention tools, WAFs, as well as visibility tools, so network monitoring, mirroring, that type of thing. And then we've also had customers talk about using things like telecom appliances, IoT appliances, and more now, SD-WAN. And one thing that customers have always asked is, how do we actually get this into AWS, get our appliances working well? And that's what Gateway Load Balancer is about. But first up, why do most customers tend to use, or a lot of enterprise customers use third-party appliances? It's usually around these 5 points. So around specialized functions, so functions that only one vendor actually creates, feature sets or combinations of features available in certain appliances. A big one is often the skill sets. So it takes a lot to train up staff on how to run a network, how to manage appliances, and actually keep up to date on a vendor's product. And if a customer is actually moving from on-prem, migrating into AWS, they've put in a big investment in building that skill set. So being able to bring that into AWS is extremely beneficial. Similar around operating processes. So if a customer has processes built around a certain vendor's product in terms of a firewall or IDS, IPS, being able to bring those processes straight into AWS without any significant change is very useful. And obviously, all of this comes down to existing investments. So investment in time, investment in licenses, they're not insignificant in most enterprises. So bringing appliances into AWS, until now, there were a few options. The most simple being the application or appliance pairs. So you would have a pair of EC2 instances running the appliance software. They'd be in a single subnet of a single availability zone, and essentially you would have a fixed amount of throughput, fixed scale. So to scale them up for more load would require downtime. You'd have to stop the instances, change the instance size, bring them back up again. They would be a single point of failure. You're running in a single availability zone. You have a single appliance carrying traffic at any one time. Not so good from an availability point of view. If you were to have multiple different applications, multiple different VPCs and accounts, you would need to replicate these appliances. So you'd need to create more appliance pairs. And of course, this will become a huge management nightmare. A second model for bringing appliances into AWS was called the load balancer sandwich. So this is quite often used to put WAFs or IDS in front of an application. So you'd have a load balancer at the front. Behind that, you would have a farm of appliances at least this time it's across multiple availability zones. Then you have your application load balancer behind it with your application instances behind that again. Quite a complex solution, quite a few moving parts to manage. Everything's got to be managed essentially yourself. Prone to misconfiguration. So if you don't have your infrastructure as code running or being deployed via a CI/CD pipeline with good testing, misconfiguration is quite probable, happens quite a bit. Again, we're talking about a single VPC, so if you have multiple apps, multiple accounts, then you're replicating this in a lot of other places, and yeah, quite expensive. And the final option was the DIY tooling side of things. So in this case, you would have multiple appliances, potentially over multiple VPCs, multiple accounts, multiple availability zones, the failover and the traffic paths all being managed by your bespoke tooling. So you would have that tooling changing VPC route tables, you'd have it moving IPs around appliances, scaling the appliances and so on. This has its own problems, not least that it's very complex. It also mixes the administration domains. So you would potentially have your security team managing your appliances as well as the tooling, and that tooling was also modifying all of your VPCs, all of your route tables. So you've got a very mixed security domain. You wouldn't necessarily know whether it's your application team which is deployed a change or whether it was your security team. And it's also very expensive. So not only do you have the cost of the appliances and the infrastructure you're running on, but all of the time and effort involved in deploying your tooling and managing and updating your tooling. So not great solutions. So as a bit of a summary of that, deploying appliances in a simple way, you end up with single points of failures. Scaling is difficult and or very limited. Quite often you have a lot of passive appliances just sitting idle. So, you know, active passive pairs where the passive one is doing nothing, and that mixed admin domain problem, which is why Gateway Load Balancer came in. So Gateway Load Balancer manages or helps you manage your appliance availability, helps you with horizontal scaling, and does the load balancing things like actually balancing flows across multiple appliances, handling flow stickiness, things like that, and also is very good on the fault tolerance front. So at a glance, what is Gateway Load Balancer? It has two components. So at the top of the diagram, we have our Gateway Load Balancer endpoint. This is a VPC endpoint, much like a standard private link interface endpoint, but with one big difference in that you can add this endpoint to a VPC route table. And that allows you to add it into your network transparently. So you don't need to do any changes to your application configuration or your instance configuration. Down below, we've got our Gateway Load Balancer, which is what it says. It's a load balancer. It's very similar to our network load balancer with a couple of exceptions. One is that it is tightly integrated with the Gateway Load Balancer, and the second is that it encapsulates all traffic between it and the targets on the back end with a protocol called Geneve. I'll cover that in a minute. So the Gateway Load Balancer handles things like scaling. So you can tightly integrate it with auto-scale groups. So as your load increases or drops, your appliance fleet grows and shrinks elastically. It handles flow stickiness. So all flows will always go via the same appliance. Sorry, the same flow will always go via the same appliance. So you've got state, so your stateful firewalls will work. We also do health checks. So in the event that one of your appliances stops working, the health check will fail, the gateway load balancer will stop sending new traffic to it, and if you've got auto-scaling configured, auto-scaling will spin up a new instance to replace it and get rid of it, and then get that added to your load balancer target group. Yeah, so at a glance, that's essentially what Gateway Load Balancer is. Deploying it is pretty easy. I'm going to do it after I go through a few slides. It's pretty simple. You create a Gateway Load Balancer and a target group of back-end appliances or back-end instances. Then you create a private link service and create Gateway Load Balancer endpoints in your consumer VPCs, update some route tables to send traffic to it, and you're good. But here's how you put it into your network. So we've got a very, very simple network. Just to illustrate, down the bottom, we've got our appliance VPC, where we've got our Gateway Load Balancer and a couple of auto-scale groups of appliances. Up the top is our consumer VPC. So we've got our source instance in a public subnet on the left, and we've got a Gateway Load Balancer endpoint on our Gateway Load Balancer subnet on the right. So just looking at the routing configuration for these VPCs, a public subnet, it's got the 10.0 route that gets added by VPC when you create the subnet, or sorry, when you create the VPC. And then it's got a default route pointing at the Gateway Load Balancer endpoint. So basically any traffic destined for this VPC will just go directly to the instances or endpoints within the VPC. But any traffic outside the VPC will be forwarded straight to the Gateway Load Balancer endpoint. In the Gateway Load Balancer subnet, we have virtually the same route table, except your default is pointing at the internet gateway up on our top right. So again, any traffic originating from that Gateway Load Balancer endpoint destined for anything outside the VPC will go to the internet gateway. Anything destined inside the VPC will just go directly to the VPC. And down the bottom in our appliance VPC, we have a single local route, which is created when the VPC is created. There's no need for these gateway load balancers to talk outside of their VPC. In fact, you can use an IP CIDR which isn't even routable for your gateway load balancer appliances. The only caveat on that is you probably want to be able to connect to them for management. So let's send a packet from our source instance up on the top left. We're sending something, a payload, our green packet, off to the internet, destination IP 54.239.17.6. That goes from the source instance to the gateway load balancer endpoint. That packet travels through to the gateway load balancer. The gateway load balancer encapsulates it in a Geneve header and puts another IP header on the top and sends that to one of the backend instances. The backend instance does what it does, whether that's inspect, firewall, what have you, sends it back to the gateway load balancer. Gateway load balancer pushes that packet back to the gateway load balancer endpoint, which then sends it on its way via the VPC routing table and off to the internet. And there's a beautiful little animation there. I can't claim credit for this slide, but the animation's kind of nice. So, and finally, I don't know why the animation comes on before the route table for the Internet Gateway. But anyway, we have an edge route table on this VPC as well, so that when traffic returns from the internet into the VPC, anything directed for the anything directed for that public subnet goes to the Gateway Load Balancer endpoint. So that return traffic will go into the Gateway Load Balancer endpoint, back through the Gateway Load Balancer, through the appliance, and all the way back into the VPC and to the instance. So, couldn't get away without a header definition here. We're talking networking. So, our Geneve packet. This is what the Gateway Load Balancer adds to the original packet when it passes from the Gateway Load Balancer to your appliance. So the original packet is completely untouched. We just encapsulate it in a Geneve tunnel header. So you'll see here we have a header protocol number. The VNI, people often ask about that when they're doing their own integrations. That always remains 0 at the moment. And then we have our tunnel options. So we've got 3 tunnel options. We've got the Gateway Load Balancer ENI ID, so that the appliances know what Gateway Load Balancer endpoint the traffic has originated from. We have an attachment ID. Currently, that's not in use. That's for some future features. And a 32-bit flow cookie. So every flow that comes through the Gateway Load Balancer is assigned a unique flow cookie. And when your appliance returns the packet to the load balancer, these tunnel options are kept in place. So Gateway Load Balancer obviously knows what flow this particular packet's from. If the tunnel options don't match, then the packet will get dropped when it returns to the Gateway Load Balancer. The other point, or 2 other points, unlike a normal TCP packet, when the appliance returns the packet to the Gateway Load Balancer, we don't swap the source and destination ports. They stay the same. The source port is a number, usually between 60,000 and 60,005 at the moment, and the destination port is 6081. So that always stays the same regardless of the direction, whether it's going to your appliances or back to the load balancer. The only thing that we swap is obviously the source and destination addresses. So, and yeah, once again, the original IP packet is untouched. We don't modify that on the way through. So it's completely transparent to the end users. So at launch, we had integrations with a number of partners. Each one of the partners on the screen at the moment built or have integrations for their appliances. So with Checkpoint as examples, if you look at their news, you'll see that they have blogs around how to integrate their appliances with Gateway Load Balancer. Well worth checking out if you happen to have those appliances on hand. We had some analytics partners involved, NetScout, Glassnostics, cPacket, that again, they all have appliances which integrate with Gateway Load Balancer, and orchestration partners. So these partners are, or they integrated with Gateway Load Balancer for the orchestration and management of Gateway Load Balancer endpoints and appliances behind them. So let's have a look at how you can put it into your network. There are a few standard architectures that we recommend. There is a blog around deployment architectures for Gateway Load Balancer. If you stick around to the end, I'll share a bunch of links with JJ and he'll chuck them in Twitch in the chat. So the most simple case is the distributed north-south routing with Gateway Load Balancer. So on our left, we've got a pretty normal looking VPC. It's got 3 subnets. At the bottom, we have our private subnets. So, that could be where your application servers, your database instances, that type of thing live. In the middle, we've got a public subnet. In that, you would potentially have your front-end instances. In this case, we've also got our NAT gateway. You'd have your load balancers, all of that kind of thing in it. And at the top, we've got an inspection subnet. So in this case, literally all that lives in there is the Gateway Load Balancer endpoint. So just looking at the routing configuration for each of these subnets. So in your private subnet down the bottom, the default route goes out to the NAT gateway, which lives in the middle public subnet. In the public subnet, your default route goes out to the Gateway Load Balancer endpoint. So basically, if you've got traffic originating from that private subnet down the bottom, it will go through the NAT gateway, get NATed, and then go up to the Gateway Load Balancer endpoint, disappear off to the Gateway Load Balancer, get inspected, firewalled, whatever it is, return to the Gateway Load Balancer endpoint, and then go out to the Internet Gateway. So in that inspection subnet, the default route there is off to the Internet Gateway. And the final route table in this part of it, or in this VPC, is the ingress route table on the VPC. So the edge route table, it has the subnet that your NAT gateway and your public instances live in. So that public subnet, that one, or the route for that, is directly to the Gateway Load Balancer endpoint. So all of your return traffic will return through the Internet Gateway, through the Gateway Load Balancer endpoint, and out to the Gateway Load Balancer and the appliances, back into the inspection subnet, and onwards to its destination. So reasonably simple. People do ask why the NAT gateway is in the middle rather than at the edge. The reason for that is at the moment you can't specify more specific routes within a VPC. So if we had that NAT gateway sitting in, or if we put the NAT gateway where the inspection subnet is and put the Gateway Load Balancer endpoint below it, return traffic would hit the NAT gateway and then go straight to the private subnet rather than going via the Gateway Load Balancer. So we have to swap it. Now we have the NAT happening before the inspection. And looking at the right side of that picture, so your appliance VPC or your Gateway Load Balancer VPC, we simply have a Gateway Load Balancer attached to 2 subnets. Inside each of those 2 subnets, we have our appliances, and we just have the local route for the VPC. Because this is the communication outside the VPC is happening via the Gateway Load Balancer, via the Gateway Load Balancer endpoint, we don't need any routing outside of the VPC at all, except for management purposes, but I'm not covering that here. So, what happens if you've got multiple availability zones? Well, you essentially replicate what you've done in your first availability zone in the second with separate route tables along the way. So you have one route table per layer per availability zone. So in this case, and we also have a second VPC endpoint. On the way back, in our edge route table, we're adding a second specific route so that anything on its way to the public subnet on the right gets pushed through the Gateway Load Balancer endpoint on the right as well. Some customers do say, well, I don't want the extra costs and the effort of putting multiple route tables in, multiple Gateway Load Balancer endpoints. I'm just going to do a single one and everything can go through that. Yeah, don't do that. That's bad. It breaks availability zone independence. If you have a problem with one availability zone, potentially you've broken the routing or there's a connectivity issue with it, then everything's down. If you have multiple sets of route tables, multiple sets of Gateway Load Balancer endpoints, you've got availability zone independence and a much more fault-tolerant design. What happens if you want to do it in multi-accounts? It's pretty easy. You just put a whole bunch of Gateway Load Balancer endpoints in each of the VPCs that you need to inspect or whatever your appliances are doing, and push them back to Gateway Load Balancer. If you're the one who's building your appliances that are sitting behind the Gateway Load Balancer, this is the point where you care about that Gateway Load Balancer endpoint ID in the Geneve packet. So you can use that ID to work out where the traffic is coming from if you need to apply a different policy per VPC or per source. Just as a point of interest, AWS Network Firewall. It was released recently. It is essentially based on Gateway Load Balancer, but it has a different approach to multi-account insertion, network insertion. So rather than having a single Gateway Load Balancer and appliance farm, you end up creating multiple network firewalls. So one in each VPC where you want to put it and its associated firewall endpoints. Obviously, managing that would be a nightmare if you're happening to do it over multiple VPCs. So you can use AWS Firewall Manager to centrally manage that policy. So you can have the same firewall rules, same firewall policies applied to multiple firewalls. So another model, if you're running multi-account or multi-VPC, is the centralized north-south routing using Transit Gateway. So in the middle here, that purple icon is a Transit Gateway. So if you're not familiar with Transit Gateway, you can think of it as a cloud router. It's essentially a virtualized device that has a whole bunch of, or as many route domains as you like effectively, and just routes traffic between Transit Gateway attachments based on those rules. One thing I didn't mention earlier, Transit Gateway, Network Load Balancer, Gateway Load Balancer, EFS, and a couple of other products, they're all based on a technology called Hyperplane. And Hyperplane is a cloud-native distributed packet forwarding engine. So while you might see a Gateway Load Balancer or a Gateway Load Balancer endpoint as a single device or a single network interface, it's not. It's actually a virtualized network function that's spread over a large or a distribution of back-end instances. So this brings you benefits, things like scale. So each Gateway Load Balancer endpoint, each NLB, they're all capable of up to 45 gigabits per second per availability zone. Brings you fault tolerance because it's not running on a single bit of hardware. Where it's multi-tenanted, it's shuffle sharded, so you don't have noisy neighbor problems. So you've essentially got very high scalability, high availability under these systems. So that's just an important note. Don't think of them, or think of them via analogy as a single device, but they aren't. So back to what's on the screen. We've got our transit gateway in the center. On our left, we've got a pair of spoke VPCs. So these are, they could have internal applications that need to communicate out to the internet, what have you. On our right, we've got our egress VPC. What I haven't shown here is the gateway load balancer and appliance VPC, because that looks identical to what we saw in the first example. It's literally just a VPC with a gateway load balancer and some appliances. So, looking at this, each one of these VPCs on the left, they have their local route, they have a default route pointing out to transit gateway, and that's about it. Inside a transit gateway, we have a single route table that allows each one of these VPCs to talk to each other, and a default route going out via the transit gateway attachment to the inspection VPC on the right. On the right, it looks reasonably similar to the distributed model, except for one difference, and that is we're able to put our gateway load balancer endpoint in the middle. We get to put it in before the NAT gateway. The reason for this is our traffic is originating outside of the VPC, so there's no confusion or there's no possibility of the NAT gateway translating the return packet and having it going directly to the source without being inspected. So I won't dive deep into the route tables here because they look very similar to what you saw before in the distributed version. East-west routing, so if for some reason you need to insert an appliance between different VPCs using Transit Gateway, the model is similar but different. So in Transit Gateway, we have two route tables instead of one. So our spoke VPCs on the left, the route table that's associated with them just sends all traffic directly to the inspection VPC on the right, and the route table associated with that attachment, the inspection VPC, allows traffic to return to each one of those VPCs. And inside of the inspection VPC on the right, we have basically all traffic being pointed at the VPC endpoint. So you can see 10.0/8, which is basically everything in the page, is destined for the VPC endpoint as soon as it arrives in the inspection VPC. And when it returns, it just goes back via the transit gateway. So this is a great way to enforce network separation using a firewall appliance, or just do inspection between VPCs using an appliance. So that's the general use case here. Okay, so let's take a look at what this looks like in real life in the console. So what I've done is taken a couple of blog posts and deployed them into two regions in my account. So we'll look at the two models. So one is the distributed model first up, and then we'll move on to the centralized model. So if you want to follow along at home, we have the blog post where you can search for this blog post, and it'll give you all the information on what I'm actually deploying. So what we have here is down the bottom, we have our appliance VPC, and that's where our firewall appliances or what have you are located, as well as the gateway load balancer. Up the top, we have our spoke VPC. And this is where our application is, and our route tables that point traffic at the gateway load balancer endpoints, also where our gateway load balancer endpoints are. What I've done is deployed the VPCs, the subnets, and a few instances. I haven't actually got the gateway load balancer or the gateway load balancer endpoints or the route table entries in there as yet. So that's what we're going to do here, just to show you how you actually build a gateway load balancer in the console. So in the console, we're in the VPC dashboard. So let's just have a quick look. In this region, we've got a default VPC, which we're not using here. We've got our spoke VPC. We've got our appliance VPC. In each one of those VPCs, let's just sort that. We have our appliance VPCs, or sorry, our appliance subnets, one in each availability zone. We're deploying in 2 availability zones here. We've got our application subnets, and we've got our Gateway Load Balancer subnets, or Gateway Load Balancer endpoint subnets. So, first thing we need to do is create our Gateway Load Balancer. So let's go into the EC2 console. I'll make that a little bit bigger so that's easier for you to see. And go to load balancing, load balancers, and create a load balancer. Grab a gateway load balancer. We'll call this Kabrog. And let's put that in our appliance VPC in the 2 subnets that are available. In this case, we only have 1 subnet in each availability zone, so only 2. And we need a target group where our appliances live. We don't have one yet, so let's create one of them as well. In this case, we'll go for instances because it's easy. Give it a name. The protocol will be Geneve because we're using Geneve encapsulation. And our VPC is the appliance VPC. So we've got a choice of 3 health checks. So we can use TCP, which literally just checks if the load balancer can make a TCP connection to your instance. And you've got HTTP and HTTPS. So with a HTTP or HTTPS health check, the load balancer actually checks that the path you've supplied, so whether that's just /index HTML or what, actually returns with a 200 return code. If that fails, then your health check fails. So we'll just leave that default. So you can set the traffic port. We can set our healthy and unhealthy thresholds, so the number of health checks that need to pass for an instance to be healthy, and similarly the number of health checks that have to fail for an instance to be marked unhealthy. We can also set the values for the success codes for HTTP, so 200 or in this case 300, so you could return a redirect and have that actually succeed as well. So we'll hit next on that. Obviously we want some targets, so our appliances, we'll select them, we'll include them as pending. So they'll be pending when the Gateway Load Balancer is created, and they will become available as soon as they've passed 3 health checks after the Gateway Load Balancer is actually running. And then we'll create our target group. So we've got our target group sitting right here. Now we'll head back to our load balancer, just refresh the list, and we've got our target group. And also, if you've got cost allocation or management tools based on tags, now's the time to add them here. And here's a summary of what we're doing, which is nice and simple. We'll create our load balancer. And helpfully, the console actually tells you what you need to do next. So you need to create a load balancer endpoint service and update route tables as well. So let's just have a look at our Gateway Load Balancer. It's provisioning now. So the next thing we need to do is go into the VPC console and create an endpoint service. So back to here. And we have endpoint services. So create our endpoint service. We've got, in this case, only one load balancer to choose from, so we'll choose that. That's the one we just created. We only have 2 availability zones because I've created it there. So they're the only, we require at least 2 availability zones to create the service, so they'll be included. If I had more availability zones in the Gateway Load Balancer, I could include and exclude them as required. We're ticking the box for require acceptance for an endpoint. If you don't require acceptance, then anybody who had the service name could just create an endpoint in their VPC, regardless of the account or anything. So obviously we want to tick that box. And private DNS is not relevant for Gateway Load Balancer. So let's create our service. Done. And so in our service, we've got our load balancer, one per AZ. And at the moment, we have no endpoint connections. So let's just go back. The thing we need next is our service name. So we'll just copy that. And we'll go to endpoints. So now we need to create a VPC endpoint in our Gateway Load Balancer subnet in the application VPC to send traffic to our Gateway Load Balancer. So let's hit create endpoint. We'll find it by name and we'll paste in what we just created. We'll hit verify and we have our service name, which is good. Now let's select the correct VPC, so the spoke VPC or application VPC. We have two availability zones. So we want to put, well, we can only create one endpoint at a time. So let's start with availability zone 2A, and we'll put that in our GWLB E subnet. We'll create that endpoint. Done. And then we want to do the same for the other availability zone. So we found our service. We'll select the correct VPC first. Then we'll select the correct subnet, which is the Gateway Load Balancer endpoint subnet in US West 2B. So we'll create that endpoint too. And that's creating now. So this will take a little while to create. The first thing we have to do though, before it actually creates, is to accept that from the service. So we go back to our service, we go to endpoint connections, and we can see we've got two endpoints pending acceptance. So we'll accept them one by one, and see that drops from pending acceptance into pending. And we'll accept that one as well. Okay, so that's our endpoint created. So we'll just wait while that's getting created. It takes a few minutes. There's a bit that needs to be provisioned on the back end before that actually becomes available and we can add it to our route tables. So just so we know what we're up to next, we will be, we'll have our Gateway Load Balancer endpoint in each one of these two subnets up the top here, and we'll create route table entries in the application subnet 1, application subnet 2 route tables, and we'll also create an entry in the edge route table. So let's go back to our console. Is that still running? Yep, still pending. So let's have a look at our route tables. Have we got them named usefully? Amazingly, we do. So we'll be working with these top three. So if we have a look at the Gateway Load Balancer endpoint route tables, we see at the moment they are assigned, or sorry, they're configured to point their default route at the Internet Gateway. If we look at the application route table, which is what I should have looked at, we will see that we just have the local route. As soon as the Gateway Load Balancer endpoint is available, we'll add our default route entry in there. So let's just see if it's come up yet. So let's just add one to default. And our target will be a Gateway Load Balancer endpoint. And we have our two Gateway Load Balancer endpoint IDs right there. What we don't know off the top of my head is which one is in the right subnet. So when you do this, you need to be aware of the route table or the availability zone of the route table that you're working with, as well as the availability zone of the Gateway Load Balancer endpoint. So this is the point where I say, don't do it by hand in production. You really should be building this type of thing using infrastructure as code. So this is all automated, so you don't have to manually make sure that you're putting the right endpoint in the right route table and so on. So we'll just pick a random one because I'm not actually going to do, I'm not putting this in a production network. So let's just pick a random one. They're both the endpoints, it's just different availability zones. So we'll save that change. So that's our Spoke VPC application subnet route table that we've done. So that would be one of these top two. So any traffic originating in that subnet is now going to be pushed out through the Gateway Load Balancer endpoint in hopefully the right availability zone. So the next thing we have to do is go back to our route tables. So that was application route table 1. Let's go to number 2. We'll hit edit on that. We'll add a default for that one. And again, point at our Gateway Load Balancer endpoint. Pick either one of them. We'll save that change as well. So both of our application subnets are sorted. So that covers the traffic path going from your application instances out to the internet. Now we need the returns. So for that, we use our ingress route table. So we've got our Spokestack IGW route table, and you can see we have an edge association with our internet gateway. So this route table is associated up the top here with our internet gateway, and it tells VPC where to send traffic to when it comes into the into that VPC. So we need to first look at our subnets. So we have our application subnets, that one, and we'll see the CIDR for this one is 10.0.1.32/27, and the CIDR for this one is 10.0.1.0/27. So we'll put two routes in there pointing at, ideally, the Gateway Load Balancer endpoint that matches to the availability zone that each one of those subnets is in. So let's head back to here. We'll look at our route table. At the moment, we have the VPC route. So we'll add one for 10.0.1.0/27, and we'll point that at Gateway Load Balancer endpoint. Then we'll add a second one, which is 10.0.1.32/27, and point that at the other Gateway Load Balancer endpoint, and we'll save that. So now we've got our route tables configured so that traffic coming back in from the internet gets sent to the Gateway Load Balancer endpoint, gets inspected, and gets sent back into the application subnet. So that's essentially how you would set it up in the most basic of deployments. So we're talking a distributed model, so where you've got a single application VPC that you're using to host your application. So the next model that we're covering is the centralized model. So using Transit Gateway as your cloud router in the middle of your environment and inspecting in another VPC using Gateway Load Balancer. Again, you can search for this or just search the internet for AWS Gateway Load Balancer blog, and you should find it. So if you have a look at this build, it's very similar in your spoke VPCs, but instead of sending traffic to the Gateway Load Balancer endpoint, we're just pushing things into the Transit Gateway. And the Transit Gateway then sends all the traffic into the appliance VPC. I won't cover actually building this, but it's built in this VPC and ready to go. So just to prove that what I have actually does something, let's look at a couple of instances. So we have, in this case, I've got 4 instances. I've got a Bastion host in my Spoke 1 VPC running. I've got a Bastion host running in my appliance VPC, just so I can get in and play. So let's just connect to the appliance one using EC2 Connect. There we go. And now let's find out what the IP of our appliance is, which is that one. There it is there, 20. So we'll just SSH to that guy. And we are there. I'm an appliance. And let's just listen for traffic coming in on our single Ethernet interface on port 6081, which is Geneve. And of course, I need to sudo for that. And probably not going to see anything for a bit. So let's go over to our application Bastion and send it some traffic. Now we need to be on our application instance, which is 10.08. Cool, so we're there, and we'll just call and we'll see if we get anything. Okay, so seeing traffic. Am I even in the right place? I am. So let's go back to here and see if our load balancer is seeing traffic and is healthy. So we have a listener on the target group. We are seeing flows come through, which is nice, which is probably just our instance calling out to NTP or something, as it does. And we'll look at our target group. We have one healthy instance. Okay, so, and it works this time. Right. And you can see in our TCP dump session here that we've got a whole bunch of traffic being dumped here. So our appliance is seeing the Geneve traffic. So you'll see source IP, destination, port 6081 on Geneve. So I did this before. We're talking networks, so it wouldn't be right without going into Wireshark. So just to illustrate what we see a source packet. It's got a destination of, or Wireshark decapsulates it, and so we see our destination out on the internet. But what actually comes through? We have an Ethernet frame, we have an IPv4 packet, which looks pretty normal, with a source address of our gateway load balancer, destination address of our appliance. We have a UDP header, source port of 60,002, destination of 6081, which again is Geneve. We have our Geneve header, which is the interesting bit, from my point of view at least. We have that VNI of 0, it's always going to be 0, and we have 3 TLVs, which is type length value, imaginatively. So 3 options. In this case, our top one is the gateway load balancer endpoint, and our bottom one is the flow cookie. So just for completeness, we'll look at this ID here, so ends in 9D7F, and let's see if we have an endpoint. There we go. There's our endpoint. So it came from this particular endpoint into the gateway load balancer. So that's essentially gateway load balancer, how it works, how you can put it in your network, and a bit of a broken demo. So, that's me. So thank you very much for listening. And here is Brian to finish us off.
Thank you, Tony. Alrighty. So, as always, we always want to know, what are the things you want to hear about? So, drop things in the chat, send us messages through Meetup, let us know if there are particular topics you're really interested in knowing more about, and we'll get presenters. Also, if there's stuff you want to present, we can do it remotely via Chime, but we've got some options here where we can get you on for a few minutes to talk about something you've done. You don't need to go for a full 45, but we're always really interested in hearing from community presenters, so please reach out to us. Submit your feedback. So Meetup is still the place to do that. You should get a little thing saying, hey, tell us what you thought. And it's just a 5-star and a couple of other buttons. Very, very quick. We do read it every month, and it helps us make sure we keep bringing good content to you. So I always appreciate that. And lastly, as always, friends don't let friends miss the Canberra AWS user group. Word of mouth is always our best mechanism. So tell people about us, share the links to our Twitch channel, share the links to our YouTube videos, let everybody know about the user group, and then we'll keep growing this little community of ours. Thank you so much for joining us this evening. Technical issues aside, I think it was a really good session. We will be back again next month, so keep an eye out on Meetup for the details, and we will see you then. Cheers.